Okay, one really important sort of offshoot or related topic while we're talking about ionic compounds is the topic of ionic hydrates. These are certain groups of ionic compounds that actually, in their solid phase, contain water molecules as part of their structure. So, if you remember that ions have these full charges, these Na pluses, these Cl minuses, the classic example of sodium chloride, but really any ionic compound has full positive and negative charges. And we've mentioned briefly that water is a molecule that is polar, meaning that it has little charges on its ends. And so, although the ions are attracted to each other, there is some space in between the ions where they can't quite pack entirely together. And water molecules are very attracted to ions. It's one of the reasons why they dissolve ions so well into solution to make salt water. But a lot of ionic compounds will actually naturally pull water in from the atmosphere when they're forming, or if you just leave them out long enough. And so they work these water molecules into their structure, and the water molecules attract them through a force that's called an ion-dipole interaction. And they're strong enough for the water to get pulled out of the air and become part of the structure. Now, the water molecules do this in a very regular way, like they do this in a quantitative ratio way. So each ionic compound, well, not all ionic compounds do this, first of all, let me point that out. Like sodium chloride actually does not do this, so it's probably not the most accurate example to use in my little drawing here. I realize that now. However, a lot of other ionic compounds do form hydrates. They do become hydrated with water, and so the underlying principles I'm talking about remain the same. But for example, when waters do join up to compounds, they do so in exact whole number ratios, or at least in exact ratios. It doesn't have to be technically whole numbers. But what I mean, if sodium chloride was a hydrated ionic compound, there would always be 2 water molecules for every 1 sodium chloride, or there would always be 3 water molecules for every 1 sodium chloride forming the unit. So in the same way that we figured out empirical formulas before, these hydrates are going to be very common questions when it comes to calculating empirical formulas, and also when we do paper 1 questions about molar mass and the number of atoms, the number of molecules, because they're a bit odd, they're a bit trickier, so that, as you imagine, the IB likes to use them as their examples. The way that we can find the data to do these calculations is that when you heat hydrated ionic compounds, and so if you ever see something written about a hydrated compound or the hydrous form of a compound, it's talking about this. It's talking about an ionic crystal lattice that has the water molecules attached as part of the structure. So if you take a hydrate, an ionic hydrate, and you heat it, the water is actually driven out of the lattice, and that leaves behind the form of the compound that's known as the anhydrate, or the anhydrous form. It's the form that has no water in it. And so if you measure the mass before and after heating the ionic compound, you can calculate the mass of water that was removed, and therefore you can calculate the moles of water that was removed. And so therefore, if you can calculate the moles of both the ionic compound and the moles of water, you can calculate a mole ratio, which is really what an empirical formula is. So just some examples. This is the name of a hydrated ionic compound. You'll often see the formulas with after the name of the ionic compound, there's a dot, a big dot, and I think some people from math class get confused and they think that it's cobalt chloride multiplied by 6-hydrate. And that obviously doesn't make a lot of sense. So please be aware that this dot does not mean multiply. It's just the convention that is used when we talk about these hydrates. So cobalt 2 chloride, well, the 2 means that the cobalt has a 2 plus charge on it. And since chloride ions have a 1 minus charge, when this formula gets balanced, you need 2 chlorides to balance out the cobalt. So the crisscross thing that you would have done previously remains the same. It has the water has no effect on the charges of the ions. The fact that this is called a 6-hydrate means that for every cobalt chloride forming the unit, so every 1 cobalt and 2 chlorides, there are actually 6 water molecules worked into the structure of this compound. So the way you'd write the whole formula out is COCl2 dot 6H2O. It's not a full stop. It's not a period. It's not at the bottom. It's a little bit higher up. So just to note that. If you heat this compound and drive off all the water, what you would have left behind is simply the cobalt chloride, cobalt-2 chloride, and that would be the anhydrous form, COCl2 with no water. So in this case, the mole ratio of water to cobalt-2 chloride is 6:1. That's why it's called 6-hydrate. And these coefficients can be fractions, but the examples that you tend to see on the IAB exam do not involve fractions. Okay, so how do we figure out a molar mass of an ionic compound? Well, or an ionic hydrate? Well, you do it the same way that you would any other compound. You add up the mass of cobalt with 2 times the mass of chlorine. However, with the hydrate, you have 6 times the mass of water. So 6 times H2O. Well, 6 times H2O really equals 12 times hydrogen, and it equals 6 times oxygen. So the molar mass of the hydrate, I'll put this in brackets because I'm simplifying it down below. The molar mass of a hydrate has to include all of the waters that are part of that structure because they are worked into the structure. There's no way of removing them when you do a reaction or whatever else. So if you want to know how many cobalt chlorides you have to take into account the fact that there's all this water in the compound with you. Whereas if you're going to do the molar mass of the anhydrate, you simply add up the mass of the cobalt with the mass of 2 Cls. So the more water in a hydrate, the larger its molar mass. So you need to use a lot more of it to get the same number of moles. Okay, so here it is worked out, 58.93, 2 times the mass of chlorine, and then 6 times water. Water as a whole thing weighs 18.02. And so you can see that in this case, the anhydrate versus the hydrate weighs more than 100 grams per mole more than the anhydrate. So it's much, much higher because of all that water. And so you'll need to use way more of the hydrate form to get the same number of moles of cobalt chloride, the actual ionic compound that's in there. Percent by mass of water in this hydrous form, well, if the cobalt chloride itself only weighs 129.83, that implies that we have about 108 grams that is water. And so if you're going to calculate a percent by mass, you always do the part. So this is the part that is H2O. And that's just from my simple subtraction. This is just the cobalt chloride mass. This is the cobalt chloride with the water. So it's 108.12 if we're going to get exact. And the whole thing, the whole hydrated form is 237.95. And then we would multiply that by 100, and we would have the percent of this compound that is water. And for the sake of time, I'm not going to do the calculation, but just like any percent calculation, you do the part, so in this case the water, and you divide it by the whole, which is in this case the mass of the hydrated compound, and then times 100 to make it a percent. Okay, you also, it's very common to see questions doing number of particles within an ionic hydrate. They love to ask about these ones, I think, because they want to make sure people know what these formulas mean. So they might just ask a simple question about what is the molar mass. We've already done one of these, so I'm going to skip this, but you just add up 2 sodiums, a carbon, and 3 oxygens to get the mass of the sodium carbonate, and then 10 times the molar mass of water, 10 times 18.02. And you put that whole thing together to get the molar mass of that compound. In order to do this, how many total atoms are there? Well, this is going to be one of those things. They've asked you for total atoms, so we're going from moles to particles, and then we're going to atoms. So in this case, 0.1 moles, and we would multiply by Avogadro's number to get to the number of formula units, which is, we're dealing with an ionic compound, so the number of particles. And then the number of atoms, we have to count the total number of atoms that are in here. Well, I've got 1 cobalt, and I've got 2 chlorines, so that's 3 from the ionic compound. But then I've got 12 hydrogens, and I've got 6 oxygens, so that's another 18 atoms. So it'd be this times 21 because there's actually 21 atoms per formula unit. I realized I just wrote FU. We're going to get over that. So in this one, it's 0.1 times 6 times 10 to the 23rd, which becomes 6 times 10 to the 22. And then 6 times 21 equals 126. So that's times 10 to the 22. And so we'd have to move the decimal place over twice to get 1.26 times 10 to the 24 number of atoms. And that might be more complicated than the examples they would give, but the basic premise of it is no different than what you've done before. The moles times Avogadro's number gets you the number of particles, and then you actually do have to count every single atom included in the waters and the ionic compound, and multiply by that number, multiply that by that ratio. Okay. They could also ask you for a specific type of atom like oxygen atoms, in which case there are 2 oxygen atoms in every one of these. So instead of 21, you'd be multiplying your final answer by 2. Right? The last thing, and also a very common thing for you to do, we'll do a lab on it, but a common question on the IB exam is to calculate the number of water molecules in an ionic hydrate. And so, as I described before, you're looking at the change in mass. So you'll be given data, the mass of the hydrated cobalt chloride and the mass of the anhydrous cobalt chloride. So if they give you those 2 bits of data, the implication is that from here to here, in order to go from hydrate to anhydrate, that means you lose water. So the difference in the mass here is the mass of H2O. So once you have the mass of H2O, you're going to convert mass of H2O into moles of H2O. So that should be fairly straightforward. That means you're dividing by the molar mass of water. You're dividing by 18.02. The key to get an empirical formula is that you're getting a mole ratio. Well, the good news is they've given you the mass of just the cobalt chloride. When they tell you that you're dealing with the anhydrous form of something, that means you're dealing with it now without the water. So this mass right here, the 4.61, is the mass that is cobalt chloride. So we've got 4.61 grams of cobalt chloride. We could divide that by the molar mass of cobalt chloride, and we'd have the moles of cobalt chloride. And we have 8.45 minus 4.61. We've got almost 4 grams. So we've got 3.86 grams of water. We're going to divide that by the molar mass, big M of H2O, and that would give us the moles that are water. Okay, when we do that, we'll have the moles of each. Okay, so actually plugging in the numbers, I took 4.61 grams, turned it into moles, which is 0.0355 moles of just CoCl2. Then taking the mass difference, which we're assuming since we're heating it, we're turning it from hydrated to anhydrated, that mass loss is the mass of water. So that's 3.86 grams divided by the molar mass of water gives us the moles of water, and that's 0.214 moles of water. This is the bigger number, right? It's significantly larger because it's in the tens place as opposed to the hundredths place. So I take the moles, and the moles on top are the moles of water, and the moles on the bottom is the moles of cobalt chloride, and I'm getting this, now it's going to give me a ratio. When I plug that into my calculator, I get the number 6, which really means that there are 6 waters for 1 cobalt chloride. And so again, that's the ratio. So 6 waters per 1 cobalt chloride. That's why I had already told you previously, it's CoCl2 .6 H2O would be the final empirical formula. So it's very similar to previous empirical formula stuff that you've done. You're converting grams into moles of both things that are in the formula. Then you're dividing by the smaller number of moles to get a ratio. And you take the number when you divide, and it's that per 1. So 6 to 1 is the ratio. And so then the empirical formula, don't forget your little dot, is cobalt chloride, CoCl2 .6 waters. And so that's the empirical formula. So we'll do some more practice with these types of calculations. But the basic things you got to be aware of. ionic compounds can contain water molecules, and if they do, they're referred to as a hydrated ionic compound. If you heat the compound, you can drive away the water and form the anhydrated or the anhydrous form of the compound. When adding up the molar mass of a hydrate, you need to include the mass of the water. It's extremely important that you do that to get an accurate number of moles. There's a sample of that. These are also common questions for calculating total numbers of atoms or particular atoms, and you do need to include the water molecules and those atoms in your calculation of total numbers of different kinds of atoms. And finally, you can calculate empirical formulas. Any sort of mass loss is the mass of water. That mass of water can be converted to moles of water. The anhydrated mass is going to be the mass of just the ionic compound by itself, which can be converted to moles of the ionic compound. And the ratio gives you the number of water molecules per ionic compound per formula unit, and that gives you the empirical formula.